Hello, and welcome to the third lecture in the series of lectures on applications of machine learning, big data, and artificial intelligence in scanning probe and electron microscopy. In this lecture, we are going to get a little bit of taste of the linear unmixing methods, including some basic linear mixing techniques and applications in microscopy and spectroscopy. In some sense, in the previous two lectures, we used the principal component analysis and some simple neural networks. In this lecture, we are going to look in a little bit into the details of these methods. So in some sense, what is under the hood of these machine learning techniques? In the first part, we are going to talk briefly why do we need linear unmixing methods and how will they help us in understanding and exploring our data. We are going to consider the simple case of the multiple linear regression for the case when we know how the individual components behave. And we will spend most of the time in this lecture discussing the principles and applications of the principal component analysis. Then we are going to get a brief idea of how does the independent component analysis works and discuss the two very important physics-related techniques, including the N-FINDR and the Bayesian Linear unmixing, and see how they can be applied for mapping phase transitions and image segmentation. Now, the important logic in this discussion would be the degree to which we can introduce the physical components in the linear unmixing models. So the idea here is that if solution exists and it is unique, it really doesn't matter how we find it. So we are going to talk about how to add the known constraints that stem from the physics of the problem in the linear unmixing analysis. Now, let's start with a brief discussion of why do we even need the linear unmixing methods in the scanning probe microscopy and in the scanning transmission electron microscopy. So the reason is that progress in the imaging methods over the last several years led to a very broad spectrum of the spectroscopic imaging techniques, where we measure the response of the material as a function of wavelengths or detection energy or whatever at each spatial location. And if we measure the spectral response at each spatial location, this gives rise naturally to a three-dimensional data set or potentially even higher dimensional data sets. So let's look at the several examples. So if you're a scanning probe microscopist, what are the examples of the spectroscopic imaging that you can regularly get access to? And one example would be the simple force distance curve measurements. You can do it on a simple microscopes. You can do it on very complex atomically resolved microscopes. You can do it in liquids. You can do it in vacuum. You can do it in ambient. But in all cases, you will have a three-dimensional data set. And then, of course, you need to figure out what to do with it. Another example from scanning probe microscopy would be the current voltage measurements. This can be the regular IV spectroscopy in ambient machines, or it can be the current voltage measurements in the scanning tunneling microscopy, so-called CITS. Or if you are an expert or practitioner on piezo response force microscopy or electrochemical strain microscopy, you are going to measure the hysteresis loops at each point on the sample surface. So this is your three-dimensional data sets. Or you can measure more complex spectroscopy when you vary the time, voltage, and maybe other parameters, and then you can have a four and higher dimensional data. So for me personally, this was how we started to get into this multivariate methods. If you are an electron microscopist, then your basic characterization technique will include the electron energy loss spectroscopy when you measure the electron energy loss spectrum at each spatial location. So this also gives the three-dimensional data set. And unsurprisingly, in the electron microscopy, the applications of the machine learning started from work by Watanabe, who applied the principal component analysis to eels. If you are an optical microscopist, you can work with the hyperspectral imaging. So notice that normal color camera doesn't work very well. It has only 3 color components. But hyperspectral cameras will detect the full spectrum. You can have a less obvious dimensionality in terms of the time resolved measurements, and you can come up with ideas of using other stimulus, for example, temperature of your sample. If you are mass spectrometry, well, secondary ion mass spectra is of course a spectroscopic imaging. So basically all microscopic measurements now allow for a broad range of spectroscoping techniques. And what is really important is that in many cases, the measured signal can be represented or approximated as the linear combination of the individual signals. This is really important. This is why we talk about the linear unmixing methods. The second thing that is very important is that very often we don't know the functional forms of the signals. If we measure the yield spectra or current voltage characteristics of some material, we sort of know how the spectra should look like, but we don't have any formula that will allow us to describe it. And the third extremely important component is that imaging methods tended to have the finite resolution, so we all know that. The important thing is that the convolution with the resolution function is also a form of mixing. In other words, if you have a microscope with a high spatial resolution, a microscope with somewhat lower spatial resolution, this resolution effect is not going to affect your unmixing process. This is why it is really important. Now, there are also less obvious cases of the linear mixing methods. So, for example, over the last several years, scanning transmission electron microscopy community is really excited about the techniques called Ptychography, where the local diffraction pattern is acquired as a function of each position. We can acquire these data sets, so diffraction pattern or ronchigram at each spatial location, but then we get the 4-dimensional data sets, which are extremely large, and they contain a lot of information about the material. So the question becomes, can we extract this material? Another example that I'm less familiar with is the focused X-ray measurements, when you also collect the diffraction pattern at each spatial location, either in 2 dimensionals or 3 dimensionals. So you can have a 5- and 6-dimensional data set. And interestingly enough, you can also use this linear unmixing methods for analysis of images. And in this case, you can subdivide the image into the subsets, and then you basically apply the linear unmixing on each of these subimages. I'll show you the examples of how we can do it, and the question becomes, what are we going to learn in this type of analytics? So, only on the location AI and the Endmembers or Eigenvectors, which depend only on the parameter variable. So in other words, this would be the spatial maps of some behavior, and this would be the spectra defining this behavior. And of course, we are also going to have some component which is noise, which can not necessarily fit in this decomposition. So imagine that you have a spatial image which has m by m spatial points. For example, in scanning probe microscopy, typical would be 256 by 256 pixels. And it has p points in spectra. So overall, we will have m squared p data points. So this is our size of our data cube. Once we separate this data set in the spatial maps and in the spectra, in principle, we also going to have up to p loading maps where the size is going to be m squared. So many of these analysis methods, they don't remove the information, they just arrange it in a different fashion. However, not all of these loading maps are going to be useful. For example, it may turn out that out of the p loading maps, only 2 or 3 have the useful information. And therefore, we can focus our analysis on the parts of the signal which are important and ignore or discard those which are not really important. And one of the primary applications for the linear mixing methods, such as principal component analysis, is actually exploratory data analysis. So let's look at some examples. So let's start with the most simple case of the linear unmixing methods where we actually know the form of the components. So this is an example of the multiple linear regression where we want to represent our unknown signal as the combination of some parameters, AI, loading maps, and the spectra, omega i's. But in this case, our omega i's are actually known. And this is the example of this study. So this is an example of the scanning transmission electron microscopy imaging of the interface between the strontium titanate, lanthanum strontium manganite, and bismuth ferrite. We can focus our electron beam inside the region which is pure strontium titanate, which is pure LSMO, and pure BFO. We can collect the spectra and somewhat arbitrarily assign them to be the known Endmembers. And that what we can do is we take the spectra in this full blue region and try to represent the spectrum and each point of this blue region as the linear combination of the spectra in this region, and these regions. So the small squares, we postulate that these are pure compositions, and the large square, we want to see what is going on. And the very interesting things happen. So if we confine our analysis to the known wavelengths range from 35 to 125 electron volts, this is where the chemical information is contained in the IL spectra. You can see that we can separate our signal in the full square as the linear combination of the strontium titanate, LSMO, and the bismuth ferrite, and we plot them as the intensity in the red, green, and blue components. So it is actually very convenient that we have three components and we can encode them in the RGB intensities. What's also interesting is that if we use the map that represents the quality of this fitting, also called X-square map, you can see that something a little bit strange may be happening at the interfaces between the strontium titanate and the lanthanum strontium manganite, and the interface between LSMO and BFO, but there is not that large. What is unusual is that if you look at the different frequency range corresponding to the energies from 5 to 35 electron volts, this is a very interesting energy range because it corresponds to the plasmons in this system. And in this case, you start to see that the error map start to show some anomaly at the grain boundary, at the interface between the LSMO and the BFO. In other words, this error map tells us that the property of this interface cannot be represented simply as the linear combination of the properties of the individual component. So there is something else going on there which goes outside of the simple chemical mixing model. And it turned out that in this case, so this is the paper that we published about 10 years ago, it turns out that in this case that at these interfaces we observe the suppression of the octahedral tilts in one of the components at the interface. And it turns out that this suppression actually gives rise to the material with a fundamentally different behavior from the bulk material. And the way we can detect it is simply from the observation of the anomaly in this linear mixing. So already it is very, very useful. Now, but what if the Endmembers are actually unknown? Notice that in the previous example, we postulated that somehow we are given the Endmembers for the pure components. But it's not always the case. So very often we really have only several examples of mixture, and ultimately we are aiming to separate the mixture in the individual components. And at the first glance, the process is really impossible. We want to separate mixture in the components without any knowledge about what the components are. So imagine that you are given a coffee with the milk, and somehow you need to separate it in pure coffee and pure milk. So how can we do that? It turns out that this is possible. There are techniques ranging from the principal component analysis, which allows us to estimate how many components are there in the mixture. We will need to use our judgment as the domain scientist to check this analysis, but PCA can suggest it. We have techniques as the independent component analysis, which in some sense is a magic. It goes against the law of big numbers. We know that if we mix a large number of components with certain statistical characteristics, we are going to get the Gaussian distribution. So ICA actually goes against the Gaussianity. We have techniques such as Bayesian Linear Unmixing and N-FINDR, which allow us to incorporate the physics constraints in the unmixing procedure. And as I said, if the solution exists and it's unique, it really doesn't matter how we get it. If we use the nonlinear unmixing method that comports to the physics of the model and our components satisfy the known physical constraint, then this solution is physically relevant. There are a lot of other methods, including the constraints on the Endmembers, the sparsity, which limits the number of components in each point, constraints on the loading maps. For example, we can request that the loading maps are smooth or have sharp boundaries. We can introduce the kernels on our transformation, so data is simplest if the physics is correct. I'm not going to talk about these advanced applications in this presentation. However, I will try to cover several examples of the PCA, ICA, and BLU as applied for the real analytics problems. Let's start with the very beginning. What is the principal component analysis? So, principal component analysis is the linear unmixing method. So we take our data cube or more high-dimensional data structure, so tesseract if you will, and we want to represent it as the linear combination of the loading maps that depend only on the spatial location and the Endmembers that, or in case of PCA, they're called Eigenvectors, which depend only on our stimulus, so wavelengths, voltage, any kind of control parameter. The important thing in the principal component analysis is these eigenvectors, omega I, are orthonormal and are arranged such that the corresponding eigenvalues are placed in the descending order by variance. In other words, the first components would be statistically more important, second component would be less important, and sooner or later you will run out of the component that matters. You would be in the pure noise space. So therefore, PCA can be used to separate the real data from noise. But in this case, we need to make a judgment about what is our selection criteria. So how do we select the right components, or how do we make the cutoff if we just choose the first several components that matter? Practically, PCA can be realized using the SVD decomposition in MatLab, on Python, or whatever. So it used to be complicated 20 years ago. Now it is just 3 lines of code. And one very important thing is that PCA eigenvectors are not expected to have a defined physical meaning. In fact, one of the early arguments against using PCA in, for example, electron microscopy was that the PCA components are not physical. And that's absolutely true. They don't. And I will show you the examples of this behavior. However, PCA is generally a starting point for many other unmixing methods, which actually do have physical methods. So PCA is where we start. Now, a little bit of history is that PCA is the orthogonal transformation that converts variables which are possibly correlated into the linearly uncorrelated principal components. It was invented in the beginning of the 20th century by Pearson, but there is a lot of earlier work, about half a century earlier, that defined the linear algebra necessary for the singular value decomposition. So as we discussed, it transforms the data so as to order the data set in terms of the variance. It reveals the internal structure of this data set, and it often allows us to do the clustering. So as usual, a great description of the PCA would be given on the Wikipedia page, or if you're interested in the historical references, you can look at this original paper by Pearson. Now, slightly more formal definition of the PCA, which is fully in the vein of the previous discussion, is that if we want to do the PCA analysis, we first find the direction in which the data changes most. So we do it by rotating the coordinate axis. After we find this direction in which data changes more, we subtract this component from the data set, and we repeat the process until we arrange the data in the sequence of the maximal variation. So the way, if you want to implement it, the program in MATLAB that allows you to run the PCA on your data set looks like this. You take your data set, which is we call data mat. We perform the singular value decomposition. This is just a function in the MATLAB. It gives us the three matrices, U, S, and V. These are the three matrices that define the PCA transform. And we transform our U matrix to give us the correct data set for our loading maps. We can plot our scree plot, which tells us how relatively important are these components. And we also get the expression for the eigenvectors that determine what our individual spectra. So very, very simple. Practically, of course, you really need to play with the MATLAB or Python code to figure out how the dimensionalities are transformed, how to plot the data, and so on and so forth. So it requires some coding experience, but it's really pretty simple. So it takes about half a day to start with your favorite data set. And most of the time will be spent learning how to transform it from initial file format into something that MATLAB or Python can work with. This is the same code which basically shows the significance of the individual steps. So this is your data. This is going to be your loading maps, which show how the data changes in place. This is your information about what is the relative importance of other components. And this is your eigenvectors. And the meaning of these components U, S, and V is the matrix that defines the rotation in the initial space, the matrix that defines the ranking of the components, and the matrix that defines the eigenvectors, which basically contain the nature of this process. Again, the Wikipedia is a great source for the information on this method, and the sources of help in the MATLAB or Python actually give you a lot of useful examples to run. So, why is it useful? So it turns out that PCA is a great tool for looking at the multivariate data, and it can be pretty much applied for everything. So this is the example of the work done by Dan Alcantara and the UC Davis, who used the principal component analysis to model and experiment with the shape of the skulls of the primates. So you can use this method to separate your data set into the individual components and see how they affect the primate shape. And again, the reason why you will use PCA for this is that it allows to reduce the large variability of the shape between the different specimens to relatively few systematic parameters. And you're welcome to learn more about Dan Alcantara's work and these publications. Now, playing with the skulls is, of course, inside the material. What we can do is take our microscope and tell it to acquire the tunneling spectra at each point on the sample surface. So we select a spatial grid which has 80 by 80 pixels. We are going to put the tip at each location on this grid, and we are going to measure the current flowing through the tip at 200 values of voltage, taken in the range from -0.5 to 0.5 volt. So if we do that, we instantly get 80 by 80 spatial grid and 200 voltage values. This is our data cube. And this data cube contains the information about the superconductive properties of this material. So, what are we going to do with it? Well, one thing we can do is take this data cube and basically average it over the voltage direction. So we essentially project it on two-dimensional space. And if you do that, you're going to get an image. So compare the orange image and this gray color image. This is roughly the same image, except that the one on the left is obtained in the normal scanning mode and has higher resolution. The one on the right is obtained in the spectroscopic mode and has a lower resolution. So it doesn't have any, once we do the averaging, there is no new information compared to the normal STM. So how can we look at the tunneling behavior? And the answer is, we are going to do the PCA decomposition. Once we do that, our data set is separated in a set of the eigenvectors. So here we show eigenvectors from first, second, third, and all the way to the ninth, and the corresponding loading maps. And we know that the first eigenvector and loading map should contain the most information about the sample, second should contain less, and so on and so forth. Now, the PCA is the purely statistical methods. We don't expect it to tell us anything about the physics of what is going on. We just explore the data. But since we are physicists, we can look at these representations and try to deduce what is that happens during this imaging. So let's look at the PCA components one by one. The first component is just the average of the IV curve. It basically represents the average topography of this image. And what you see here is essentially a low resolution version of the atomically resolved image. Now, the interesting things happen in the second and third component. Again, they don't have a rigid physical meaning, but once we look at them, we can conclude that the second component sort of defines the band gap in the material. If you imagine the combination of the first and second component, you will see that the IV curve will become slightly broader. So the third component is roughly the shift of the IV curve. So this is one is the expansion and contraction of the band gap. The third is the shift of the band edge. And what is interesting is that once you look at the first, second, and third component, you can clearly see topographical features. So in other words, they are not random. There are multiple atoms that participate in formation of these collective features. So we actually learned something about the electronic structure of the material. We don't know what it is exactly, but we know that it is real. Now, what about the high order components? If you apply the same logic of looking both on the eigenvector and loading map, you can see that the component number 6 seems to have some non-trivial behavior. So this is clearly not a noise. But the components number 4 and 5 start to look like some form of the periodic noise that is being captured by the microscope, and that the principal component analysis allows us to separate. More interestingly, if you look at the eigenvectors for the components 7, 8, and 9, you can see that they're actually dominated either by noise or by some form of rapidly changing signal. So based on the physical common sense, we can say that this is probably not something that corresponds to physics. This is probably the microscope problem. And if we look at the loading maps, we can see that this is exactly true. So these loading maps don't show any spatially resolved features. They show essentially the noise pattern. In fact, for the last component, component number 9, you can see that it is all concentrated in one spatial pixel. So it's definitely the microscope problem. Maybe somebody entered the lab and slammed the door. So this gives us the initial idea of what the principal component is good for and what it is not good for. It's a great way to explore the data. It's a great way to denoise the data. It turns out that it is allows us to decouple the 60-cycle noise or more complex noises remarkably well. We can just use the components that don't have noise to resynthesize the signal. And in many cases, it gives us some insight about what is the relevant physics in the system, but it's only insight, it's not a proof. So we really need to analyze data in different ways, which we can do now because now we know what to look for. This is another and slightly more complex example of the PCA on the atomically resolved dataset. So you can see here that you have a high resolution image. You have the spectroscopic dataset, which we again project on the two-dimensional space. You can see that variation of the IV curves at different locations are actually pretty small. This previous dataset, we made a judgment that these components are important because they clearly show features that span multiple atoms. We can formalize this somehow by calculating, for example, the spatial correlation functions and plotting the spatial correlation function as the function of the distance. So this is the example for atomic force microscopy data, but the idea is essentially the same. So you can see that for the small component, for example, component number 1, 2, and 3, there are the long-range components in the correlation function, meaning that there are real features in the image. At the same time, for the correlation functions, which are somewhere between 20 and 40 components, they're just zero, meaning that our loading maps don't have any spatial correlations and therefore don't have any features. So these are the components that don't have any spatially resolved information, and in principle we can disregard from the analysis. What's interesting though, that in this particular experiment, the component number 8 and component number 17, and even these components, which are between 40 and 50, they have a long-range correlations. And very often we can look at the specific maps and find out that there is some subtle physics of the sample that is very, very weak, but nonetheless can be detected by the principal component analysis. And this capability to select very weak spatially correlated signals from much stronger non-spatially correlated noise or random signal is something that makes principal component analysis very, very valuable. Now, does the PCA match physics? And the answer is generally no, but there are some cases when it does. And this is the example of the principal component analysis as applied for the band excitation scanning probe microscopy. So band excitation SPM basically measures the full amplitude frequency curve of the cantilever. And it turns out that if our variation of the signal within the image is very small, for example, like in this dataset, of this order dataset, it turns out that the principal component components look almost the same as the variational derivatives of the response function of the system. And the reason why it happens is very simple, because the variational derivatives are orthogonal by definition, and the principal component analysis are orthogonal by definition. So in this case, we have a matching between physics of the SHO process and the PCA eigenvectors, and therefore they resemble each other. That actually happens more often than not, and sometimes it gives you valuable clues as to how your microscope works, but this is rather unusual. So most of the time, principal component analysis is a great way for the exploratory analysis of your data, but it doesn't offer any physics connections. And if it does, it is worth paying attention to it. So this is actually another very interesting example when we applied the PCA for image analysis. But what we did in this case is we took an image of the surface domain structures in some ferroelectric material, and we tried to answer a question whether we can use the principal component analysis of the Fourier transform to find the hidden periodicity in this image. So what we do is we take this sub-image and create the Fourier transform of this sub-image. We shift it by some number of pixels and create a second Fourier transform, and keep doing it until we have a set of 2D Fourier transforms which are sitting on the spatial grid. And then we perform the PCA analysis of these Fourier transforms and we look at the results. So these are the loading maps. They look like they allowed us to get some insight in the periodicity, even though we cannot say much about it. But what's interesting is how the eigenvectors look like. So they start to look exactly like a type of s orbital, 2 pi orbitals, several d orbitals and f orbitals and so on. And the reason for that is exactly because we have a hidden periodicity. So this is the diameter of this ring in the Fourier transform is the periodicity of this domain structure. And these components are simply the result of how the PCA work on this type of system. So these components needs to be orthogonal and the shape of the orbitals are orthogonal. So it's very interesting observation. We cannot learn much out of it, but it's a beautiful demonstration of how the statistical analysis works on imaging data. Further in the presentation, I will show you several examples when we actually managed to learn something useful out of multivariate analysis of images. But it requires more complex analysis methods. Let's move on. So what about other analysis? And in this case, the analysis is the independent component analysis. And this is how it compares to the PCA. So PCA gives you the orthogonal transform of possibly correlated variables in the set of linearly uncorrelated components. The ICA is the method for separating multivariate signal into the additive components, assuming statistical independence of the source signal. So in some sense, it goes against the law of the big numbers. And a typical example of the ICA is so-called the blind source separation or cocktail party problem. Imagine that you are in the room with a lot of people. Every one of them is talking. Somehow your brain is capable of focusing on talking just to one person and understand what this person is telling you, despite the fact that a lot of people talk around and they can be even more loud. So slightly more mathematical form, the goal of the ICA is to transform the observed data into maximally independent components, which are independency being defined through some function which of independence. And if you do that, then you represent your data as the linear combination of the sources, which are mixed by some value, some metrics. Again, the great source of information on the ICA is the Wikipedia page. And this is again slightly more formal definition that if our data is the set of vectors, for example, the time traces, which is mixed via some matrix, what we want to find is both the mixing matrix and the sources. So this can be calculated by calculating the weight vectors and the cost function that maximizes the non-Gaussianity, so we go against the law of big numbers, or minimizes the mutual information between your signals. So in other words, giving this cocktail party example, you are listening to only one person about who talks about one topic. You don't listen to the person standing next talking about something totally different. So the ICA is not as easy to use as the principal component analysis, but there are a lot of available algorithms either in scikit-learn or fast ICA developed by Ephoch and many other tools which are available now or will become available in the near future. Now, this is kind of the humorous representation of how does the ICA works when you have several sources, they're mixed together and into one signal, and you want to separate them. So the question is how are you going to do that, and what is going to be the outcomes. It has recovered the rectangular signal, and it even recovered the triangular wave, but of course only up to the phase. So instead of going up wave, it is going down wave. So still not magic. But this is really impressive, and this capability of recovering the individual components for the time-dependent slots is a real power of the ICA. So experimentally, it was applied a lot in the problems like chemometrics or whatever. So this is an example of ICA being applied to the mass spectrometry data sets. And in this case, it allowed to extract the signature of the individual components. But as applied for the SPM and electron microscopy dataset, the results were a little bit mixed. So this is the example where we try to use the ICA as a part of this sliding Fourier transform approach to find the periodicity in the system. And we found out that it doesn't work this well. And the reason for that we speculate about, is that ICA works against the Gaussianity. So it needs to have several sources where we want to minimize the mutual information between them. When we work with the scanning probe microscopy or electron microscopy data, we virtually always have to deal with the sequential data acquisition. So we collect our information pixel by pixel and then line by line. So the basic principle of ICA, or the basic idea of ICA, is just not realized in this case. So it can still produce good results, but most of the time over the last 10 years, our observation was that ICA is not particularly well suited to the physics of the scanning probe or electron microscopy imaging. Situation can be completely different if we have the multi-channel detections, which is synchronized this time. There ICA can be extremely useful, but for the time being we haven't dealt with this type of problem. The Endmembers. But in this case, our eigenvectors satisfy a very important property, which is that they are non-negative. So each of those is more than 0. That means that they already start to have a physical meaning, because, for example, if we detect a signal from the photodetector or the EELS camera, the signal can be only positive. PCA component will give us the second component always negative, piecewise negative, because of the orthogonality constraint. So the Bayesian linear unmixing, techniques such as the non-negative matrix factorization, or techniques such as N-FINDR, allow us to keep the signal positive. And the second thing about the BLU is the loading coefficient sum to 1. And that's really important because it instantly starts to remind you of something from the field of thermodynamics and phase diagrams. So if we represent the properties of the system as the 3-component phase diagram, that at each of those locations, the loading coefficients, or the molar fraction of the system, sum up to 1. So in some sense, BLU is ideally matched to the physics of the phase mixing problems. And I will show you the example of when we actually applied it in this capacity. Now, practical implementation of the BLU can be done through the codes written by Nicolas Dabijon about 10 years ago. So he used a pretty complicated combination of the N-FINDR, or finding the simplex for the PCA space, with the Markov chain Monte Carlo in order to find the BLU components. So the technical details are available in this manuscript through the piezo response force microscopy, which gives us domain structures. And we can also do the micro Raman measurements, which gives us the information about chemical and physical properties through the Raman spectra. And interestingly enough, we know that the Raman spectra for the one phase and another phase are slightly different. So these are the example of 2 phases. But the difference is very, very small. If you look at this red and blue spectrum, most of the peaks are exactly the same. So this big peak, this set of peaks, the difference would be only in the relative intensities or in the presence of relatively small peaks inside the material. So the question becomes, can we explore this material using the phase transition of this material. And the idea here was that we can use the laser in the micro-Raman heater in order to heat the material and drive it through the phase transition. And this is the example of the PFM amplitude and the PFM phase once we are ramping up and down the laser power. And you can see if the laser power is large, then our signals start to become weaker, which basically means that we heat the material above the phase transition temperature and it becomes less ferroelectric. Then we asked ourselves a question, can we use the same approach, so we heat by the laser, in order to study the evolution of the Raman spectra through the phase transition? So why is it a problem? It's a problem because it's relatively easy for us to get this Raman spectra, but it is very difficult for us to figure out what this even means, because you can see that on increasing the laser power, the spectra change in the systematic fashion, but they still remain very complicated and we sort of don't know what they represent. We cannot ascribe the intensity or shape of the peak to some specific composition. And this is the case where the Bayesian linear unmixing works like a magic. All we have to do is to take our collection of spectra over multiple temperatures. We know that there are only 3 components in the systems. So we know that because we have the ferroelectric phase of the layered material, non-ferroelectric phase of the layered materials, and the second non-ferroelectric component. So we can kind of postulate those. Therefore, we can take our data set, perform the Bayesian linear unmixing, and we get the spectra of the components, and we also get the laser power dependence of the relative fraction of those components. And you can see that the black component have only a weak change with the laser power. The blue component exists at low temperature and then it starts to disappear at high temperature or high laser power. And the red component does not exist at the low temperature but start to appear at the large temperature. So what it tells us is that the black component is this nonpolar indium-based phase. The red component is the paraelectric material. It appears only above the phase transition. And the blue component is the ferroelectric phase. It appears only below the phase transition. So using this Bayesian linear unmixing and knowledge of the property of the material, we can basically separate this data into 3 components that have a well-defined physical meaning. So we don't know what the individual spectra mean in a sense of what phonon mode each peak corresponds to, but we can already use it to do a precise mapping of this material and study the phase transitions on the local level. Now, this is another example of the application of the Bayesian linear unmixing for the microscopy data. And in this case, we apply it to study the conductive behavior in the first order hysteresis reversal curve measurements. So what we do in this case is that imagine that we apply the voltage that goes like this increasing waveform to the probe. And while we are doing it, we measure the current flowing between the AFM tip and the surface. If the system is purely physical, so there is no chemical processes, the current flowing forward and backward would be exactly the same. So there would be no hysteresis in the IV curve. If, however, application of the large bias induces some chemical changes in the system, then our hysteresis curve will actually open up and the forward and backward IV curve will be different. So the reason why we're choosing this type of complex waveform is that each of the sub-elements checks whether the forward and reverse curve coincide. So in some sense, what is the size of the hysteresis? And we progressively increase the magnitude of those in order to find out how our hysteresis loop area changes with the limiting bias. So, and in principle, this should allow us to analyze the onset of chemical reactions, kinetics, and so on and so forth, in theory. This is the example of the material system where we apply this method. So this is the cobalt ferrite layers, tubules, grown in the bismuth ferrite matrix. And the remarkable property of this is that the interface between the cobalt ferrite and bismuth ferrite have the electroresistive properties. In other words, as the function of the electric bias, we can make these regions conduct, and we can make these regions insulating. And as shown in this data set, we can have around one pillar, we can have all four interfaces conductive, we can turn one off, and now only three are conductive, or in this case only two are conductive, or it is the other two. In this case only one is conductive, and in this case none is conductive. So in some sense each pillar behaves like it has four parallel conductive channels that can be turned on and off individually. And this is a work of my good colleague Eddie Chu in Taiwan, which was published about 6 years ago. Question was, can we learn a little bit more about this material and conductive behavior using the Bayesian linear unmixing and the FORC IV dataset? And of course, we can make the measurements, so we can get the FORC curve at each point on the sample surface. So now we have a four-dimensional dataset where at each pixel we collect the FORC IV curve. Then we can look at it. We can look at the average data, which is essentially current maps, or we can look at the maps that represent the hysteresis loop area. And one thing that we instantly notice is that these data sets are very noisy. So if we look at the hysteresis, it's small. We kind of see that the hysteresis is enhanced around the boundaries between the tubules and the substrate, but data set is noisy. The question is, what can we do? We clearly have a variability of conductance and loop opening, but we also have too much data. So we have a four-dimensional data set. How can we represent it? What's in there? And it turns out that the Bayesian linear unmixing is the ideal method to study this material system. So if we explore the statistical behavior of our data set, we can show that the data variation here can be represented exactly as four components. One would be ohmic component that's localized within the grains, the nonlinear component that's localized in the different parts of the grains, the essentially zero current component, which is concentrated in the substrate, and the hysteresis will exist only in one of the components, which is actually localized at the boundaries between the grains and the matrix. And in fact, we can show that if we increase the number of components, we can continue splitting only these components in more in statistically variable behaviors. These ones remain pretty much the same. And it turns out that in this case, the Bayesian linear unmixing is the ideal tool that matches precisely the physics of the problem and allowed us to systematically study the behavior of conductivity in this system. Different Bayesian components can be described by different physics models. So this was a basically manual analysis, but in the future something like this can be used by the better techniques such as the Bayesian statistical inference and so on and so forth. But the big idea is like this. We measure the conductivity in the tip surface system. We can separate it into the independent component by the statistical analysis. We know that in this case the principles of the statistic analysis, the additivity and non-negativity, correspond to the physics of the problem, and therefore we can expect that our statistical components have a physical meaning and can be fitted to the physical models that tells us what the material's parameters are. So as the machine learning and linear unmixing tools progress, we can do this type of analysis using more and more sophisticated machine learning tools, but that was kind of important to start. Now, what about other data sets? So can we use the Bayesian linear unmixing for the CITS datasets or tunneling spectra? The answer is, of course, we can. So in this case, we no longer have the problems with the negative components as we did with the PCA. However, we still don't have any physical meaning behind the tunneling spectra. So in some cases, it is possible to qualitatively identify them with the specific physical mechanisms, but this is assignment utilizes primarily the intuition of the operator more than anything else. What about other methods? So I mentioned to you the technique called N-FINDR, which is in some sense equivalent to find the simplex in the linear space of the principal component. So the minimal shape that allows us to minimize the volume that the system occupies in the PCA space. So in this case, we still have the physical constraint that our components add up to 1. And an example of using the N-FINDR for the realistic material system is given here. So now we are going to see how this method can be applied for image analytics. Imagine that I have an image which has two components. So one component has one periodicity and another component is having a smaller periodicity. And I want to automatically separate this image into this part and this part. In slightly more scientific terms, this means I want to perform the segmentation of the image based on the periodicity. And as you can imagine, realistically, this segmentation can be used to find the individual phases in the electron microscopy data or different regions in the scanning probe microscopy and so on and so forth. So what can we do? What we can do is to use this approach with the sliding window. So we have a small window, we slide it across the sample, we perform the Fourier transform, and then we apply the N-FINDR on our stack of the Fourier transforms. And the idea here is twofold. So first of all, we know that Fourier transform amplitudes are non-negative. In other words, N-FINDR in this case matches the physics of the problem. And second problem is that the Fourier transform, once we do the Fourier transform and get rid of the phase, it removes the translation. So the translation in the periodic structure is equivalent to the phase shift. And if we remove the phase, then edge effects of course matter, but we don't have to deal with the translational behavior, which allows us to separate the data into the Fourier transforms of pure components. And this is how it looks like. So this is our one end member, and this is our second end member. If you can look at this, you can clearly figure out that one of them corresponds to one phase, another corresponds to a different phase. And this is how our abundance maps are looking like. So we can clearly perform the image segmentation based on this sliding window Fourier transform followed by the N-FINDR. What's interesting is that we can see how the system behaves if we try to artificially explore the effect of the number of components. We know that the ground truth is that there are only two phases in the image. If we perform this analysis, when we postulate that there should be two phases, we of course separate one phase and we separate the second phase. If we postulate that there should be three phases, we will separate one component, second component, and then our analysis will zoom in on the interface region as the kind of third component. And you can see how the Fourier transforms look like in this error component or interface component, the first component and the second component. And if we try to insist, for example, we tell the system that algorithm that there should be four components, in this case we still have one component and we have the interface, but then the algorithm tries to separate one of the components in the subcomponents, and you can see that it doesn't look very well. So based on how these maps look like, we can make a judgment about how many components we need to choose to make the proper segmentation of the image. This is the example of the real data rather than simulated data. So this is a catalyst particle which has one phase and it has a second phase. And you can see that this data is rather beautiful, but imagine that if somebody tries to ask you, is this one phase or two phases? For example, is this a new phase or just the example of the same phase as this one? Or if somebody asks you to count the number of atoms in this composition and this composition, that's really unpleasant. So this type of problems are better analyzed using the machine learning methods. And this is the example of this sliding FFT N-FINDR analysis as applied for this material system. You can see that our analysis clearly separated one component, second component, the empty space, and these are the Fourier transforms corresponding to these individual phases. And you can see that the more ordered phase has a beautiful Fourier pattern, and this phase is actually much more amorphous. The Fourier components are more ring-like, which reflects the high level of the disorder inside this composition. So in this particular case, in the previous case, we utilized the fact that in the chemical system, two phases cannot coexist in the same place. So it's either phase 1 or phase 2. You cannot have it two at the same time. This is not necessarily the case for the physics problems, because in physics, the periodicities and orderings are described through what is called the order parameter. And these order parameters can actually coexist. For example, if the system has some periodic distortion in x direction, it can also have the periodic distortion in the y direction at the same time. And it turns out that in this case, we can also use this N-FINDR approach to look at the complex system. So in this case, it's a scanning tunneling microscopy image of ruthenium trichloride, a very famous material with the Kitaya physics. We can look at this material and find the individual components and separate them using this method. And we can create the real space abundance maps, which now tells us the spatial regions in which the regions with the certain order parameters are concentrated. And in fact, we can do the inverse Fourier transform and find out what are the structural representation of what these order parameters are. So it turns out that one of them is actually a hexagonal superlattice, and another is the dimer superlattice, and that's actually fully comports to the known physics of this material. We just managed to separate our image where the physics of different phenomena is mixed into the individual components without knowing a priori what these components were. And this is really truly exciting. How does this N-FINDR compare to ICA? So this is the example when we perform the ICA Unmixing of the sliding Fourier transform and N-FINDR of the sliding Fourier transform. You can see that N-FINDR works extremely well and ICA does not, exactly because in one case the method satisfies the physics of the problem and in the other case it does not. So here is your argument. You can learn more about these methods in this set of papers. So they represent the use of the Bayesian Unmixing for different type of problems, ranging from phase identification in the metal insulator systems, beam-induced phase transition, applications for techniques such as high-energy electron diffraction in the epitaxial growth processes, and so on and so forth. What else can we do? So one of the areas which grows very fast now is the so-called 4D stem, or the subatomic diffraction, where we use the diffraction from our electron microscope beam in order to explore the structure of the material on progressively smaller length scales. And what's interesting here is that in case of the electron microscope, the size of the electron beam can be actually much smaller than the distance of the atoms. And in some sense, you have a diffraction when your distance between the scatterers is much larger than the excited volume. So in some sense, it's a diffraction in the wonderland. This is how it goes. So imagine that you have a diffraction using the plane wave. So you have a well-defined Fourier peaks that you can clearly see. This is a classical Fourier transform. If you make your beam smaller, then your peaks start to broaden. This is a kind of broadening of the Fourier peaks and formation of these disks. Once you keep doing it, then the disks start to overlap, and ultimately you go to the situation when your width of the Fourier peak becomes larger than the distance between the Fourier peaks. So they give rise to a very complex interference pattern. What's important is that this pattern contains a lot of information about the material, but you also have a lot of data, because once you do the measurements like that, you determine a pattern very close to one atomic column, a little bit further away from the atomic column, and so on and so forth. So you get a four-dimensional data set, and the question is, what are you going to do with it? Turns out that the linear mixing methods work remarkably well in these cases. So this is the example of the principal component analysis for such data. When you have our data set, we determine how many of these components are useful. We determine how the individual components look like, and we determine how the spatial loading maps look. And this, of course, is the exploratory data analysis. It doesn't explain us what the physics is, but at least allows us to work with these data sets and get some systematic insight into what goes on. And you can learn more about this particular effort in this paper published about 3 years ago. Now, what else? So we talked briefly about the PCA, N-FINDR, Bayesian Unmixing, and ICA. So is that all? The answer is of course not, because what we need is the unmixing or decomposition methods that are infused in some universal manner with the a priori physical knowledge. So the trivial example is the non-negativity or additivity to 1. The less trivial one would be that the N-member should be close to some expected behavior. So if we do that, our resultant components can be directly interpreted in terms of relevant physics. So we've done it in the Bayesian unmixing by the constraints of N-members. We can introduce the sparsity. We can introduce some constraints on the loading maps. And there are very interesting directions related to so-called kernel transforms, where if the data has a kernel has a correct functional form, then the data would be simplest. This is extremely exciting direction, and stay tuned for the further lecture. So the next lecture we are going to talk about the applications of the machine learning methods for the image analysis and scanning probe microscopy, and maybe with some examples of electron microscopy as necessary. Stay tuned.